So far, we have looked at the response of resistors, inductors, and capacitors to DC sources, and we also looked at what happens when you apply a square wave as the input. Now what we're going to do next is we're going to start looking at what happens in the presence of an AC source. So this section is the AC response of R, L, and C. So let's first quickly talk about what we mean by an AC source. So we are looking at a voltage E, which is of the form E0 sine omega t. What does this look like as a function of time? So this is a sine wave in time. The amplitude of this wave is E0. And if I call the frequency, or if I call the time period as t, here's the time period, or this is the half time period, then omega is 2 pi divided by t, or you can call it 2 pi f, where f is the frequency. So omega is often called the angular frequency, whereas f is generally just called the frequency. So this is what a sine wave looks like, and we are going to look at inputs in which we're going to look at circuits in which the input looks of this form. So we're talking about AC inputs, and then we will put whatever inductors, capacitors, resistors, and so on. So let's do the three of them in detail. So first we'll do response of R in an AC circuit. So what we're looking at is a circuit that looks like this. The input that we're giving it, as I mentioned, is E0 sine omega t. And we know that the potential difference across a resistor V, or in this case I should call it E, is I times R. So I is just E0 over R sine omega t. So if I want to plot this, this is the sine wave that we had plotted before for E. And what does I look like? I, the current, is also a sine wave. It has the same frequency. It just has a different amplitude. So if I can call this I0 sine omega t. So the amplitude of the current wave is I0, which is E0 divided by R. But apart from that, it has the exact same shape because this is also sinusoidal. So it might look something like this. This is I. So what we say is that the current and the voltage are in phase. In phase means that they have the same, they both become zero at the same time, they both have maxima at the same time. So they are perfectly in phase with each other. There is no phase difference between them. So that is it for the resistor. Whenever you have a resistor in an AC circuit, the current and the potential difference across it are always in phase. But now let's see what happens if we have an inductor. So now our circuit looks like this. And E is E0 sine omega t as always. Now potential difference across an inductor is L di by dt. So in order to find the current now I'm going to have to integrate. So L di is E0 sine omega t dt, and if I integrate this I get L I is E0 divided by omega. Integral of sine is negative cosine. So I is E0 over omega L. Cosine of omega t is sine of pi by 2 minus omega t. So this is because there is a negative sign over it. Is that correct in my notes? Yes. So I can call this I0 sine of omega t minus pi by 2. Now let's see what this looks like when I plot it. So as usual, I have my sinusoidal E, and now the current goes as sine of omega t minus pi by 2. So it is a phase difference of pi by 2 behind the uh, EMF, behind the voltage. So it looks something like this. This is my I. So what we say is that when you have an inductor, then the current lags the voltage by a phase difference of pi by 2 or 90 degrees. Important word over here is it lags. So the current lags the voltage, means it is behind the voltage by 90 degrees. One important thing that I want to bring your attention to over here is that normally we think of I0. So over here you see I0 is, we have defined it as E0 divided by omega L. So what this means is that this quantity omega L is kind of like the resistance of an inductor. It is the effective resistance of the inductor. So omega L is effective resistance of inductor, and we have a special name for this. It is called the inductive reactance. And it is given the symbol XL. So XL is omega L, and this is the resistance, the effective resistance of an inductor. So of course this has units of resistance itself, it's measured in ohms. And 1 over XL, which is like the conductance, is called the inductive susceptance. So XL is like the resistance, and 1 over XL is like the conductance of an inductor. Now let's look at the same thing again, this time for a capacitor. So this time our circuit looks like this. So E is E0 sine omega t. And for a capacitor, we know that the charge across it is given by C times E, or C times E0 sine omega t. Now I want to find what the current is, so I need to differentiate this with respect to time. So I get C E0 omega, and derivative of sine is cosine. And if I want to write this in terms of a sine wave, I write this as E0 divided by 1 over omega c sine of because sine of 90 plus theta is cosine theta. Yeah. And I'm going to write E0 divided by 1 over omega c as I0. So this is the current across the capacitor. How does this look graphically? Once again, sine wave for the voltage. This time, the phase over here, the argument of the sine function is omega t plus pi by 2. So this is ahead of the voltage. So this looks something like this. So this is I. So this time we say that the current leads the voltage by a phase difference of pi by 2 or 90 degrees. And here the important word is leads. So the current is 90 degrees ahead of the applied voltage. Now once again, we can define an effective resistance, but this time for the capacitor. So I0 is E0 divided by 1 over omega c. So now this 1 over omega c plays the role of this effective resistance of the capacitor. So we define xc as 1 over omega c, and we say that this is the effective resistance of the capacitor, and we call it capacitive reactance. And 1 over xc, we call it the capacitive susceptance. All right. Now what I want to look at after this is the power response of these elements to an AC source. Power response. Now usually in electrical circuits you have probably seen that power is given by voltage times current. So in our notation it is E times I. So but in our case the voltage and the current are both functions of time. So we are not concerned with instantaneous power, we are concerned with an average power taken over time. So average power, which is average of EI. This is what we are interested in. So let's look at first the resistor. For a resistor, we have seen E is E0 sine omega t, I is I0 sine omega t. So P, which is the product of these two, is E0 I0 sine square omega t. So average power is E0 I0 and average of sine square omega t. Do you know how to take averages of functions? So in general, let's do a short aside over here. Suppose I have the function, suppose I have some f of theta. Then if I want to find the average of f when theta goes from 0 to 2 pi, let's say, this is going to be integral from 0 to 2 pi of f theta d theta divided by 0 to 2 pi of d theta, or so this is the formula for taking average. So you can just verify these results. If you take the average of sine square theta, then you get half. If you take the average of sine theta or cosine theta, or in general any sine n theta or cosine n theta, n being a natural number or an integer, this is 0. This you can probably see intuitively because integral is just area under the curve. So if you are taking an entire sine wave or a cosine wave, then there's as much part of the wave above the x-axis as there is below it. So the average has to be 0 in the end. So we're going to use these results. So where, as you can see, we have the average of sine square of omega t. So when we integrate this over an entire period, we get half. So because there is, so this is the power that is dissipated by a resistance in the circuit. So we say that a resistance is a dissipative element. Normally in a circuit, if you have a resistor with this AC source, then the resistor will generate this amount of power and it will get dissipated away as heat. Now let's look at the power response of an inductor. Now for an inductor, we saw that if you take E as E0 sine omega t, then I turns out to be I0 sine omega t minus pi. No, let's write this in terms of the cosine, it will be easier. So what was it in terms of cosine? I think it was negative cosine. Yes, negative cosine. So now power is EI, which is minus E0 I0 sine omega t cosine omega t, which I can write as so now if I take the average power, it is, see now this is not a sine square, this is sine 2 of omega t. So the average of this is 0. And we can do the same thing with a capacitor. Where E is E0 sine omega t, I is I0 positive cosine omega t this time. So the power is, just cutting short one step, so average of P is once again given by the average of sine 2 omega t, which is 0. So based on these two, we say that inductors and capacitors are non-dissipative elements.